So before I clear this out, I just kind of want to refresh and say, listen, what we did in the last video is we were talking about electrophilic aromatic substitutions. And this was the general template that we went through to talk about how these reactions went forward. So in the beginning stages, it was an addition reaction. We broke a double bond. We disrupted the delocalization. We brought a nucleophile into the picture at that point. That nucleophile had two options: to sit on top of the carbocation, and that would truly disrupt the delocalization, and the benzene's not going to go for it. Or route number two, pull a hydrogen off that can easily be donated and take those electrons from the bond, shove them back into the ring to recomplete the delocalization that was there prior. And that is exactly what happens with all of these. So that is why we call this a substitution and not an addition reaction. So I keep telling you there's five, right? There's five benzene reactions. Okay, so let's name them. 1, 2, 3, 4, and 5. 1, it's going to be a halogen. So we call this a halogenation. Oh, go figure. Not rocket science. Halogenation. Number 2 is going to be nitration. What do you think it's going to add on? Nitro. Okay, yeah, good. See, again, it's not very difficult. Number 3 is going to be sulfonation. What do you think it's going to add on? A sulfur-containing group. Well, we're on a roll, folks. And number 4, what else are they going to throw at us? Well, number 4 is going to be called a Friedel-Crafts acylation. Oh, no. Oh, no. Friedel-Crafts acylation. What in the world? And then number 5 is going to be called a Friedel-Crafts, gosh, 2 reactions named after them? Yeah, that's right. Alkylation. Friedel-Crafts acylation, Friedel-Crafts alkylation. Well, you already know that's going to be confusing. Well, it shouldn't be, though, because you need to use your words. That's what I keep telling you over and over. That's what I told you in 251. Acylation and alkylation are different. They're different terms. What does alkyl mean? You know that. What's an alkyl group? What does acyl mean? Well, we've seen that before. We should know what an acyl group is, but we'll talk about the differences when we get there. So these are the 5 reactions with just a normal old benzene. And folks, that's it. Those are the only 5 that we're going to mention with just benzene. So the way that I need you to think about this is benzene is an awfully snooty compound. That molecule, ew, that's how it looks at everything. I don't need you. I can do it on my own. Nope, not interested. Nope, another day. Sorry, yeah, I'm busy. That's benzene. Benzene's very stubborn. Benzene doesn't need to react. Benzene doesn't need to go anywhere. Benzene doesn't need to see anybody. Benzene probably has no social life. It's just a boring old molecule. Are you a benzene? Well, however, we can get the juices flowing. And we get the juices flowing of benzene by choosing one of these 5 reactions on the screen. This is how we get that benzene to react. It's got some interest, right? Hey, you want to go play video games? And benzene goes, what? Of course I do. Or, hey, benzene, you want to go to the beach? Oh, yeah, I thought you would never ask. That's the attitude of benzene. Only these 5 things will get benzene's attention. Pretty much. No, I'm overgeneralizing stuff, but for our sake, this is really all that we need. So we're going to have to take these one by one, and we're going to go through and talk about these reactions and talk about what kind of products get formed and maybe a little bit about the mechanisms of them in order to get to that point. So we're going to start off with halogenation first. Okay, so what is a halogen? Fluorine, chlorine, bromine, iodine. Ding, ding. That's right. Good job. So that means benzene can be halogenated. And quite honestly, I've always told you, 251, 252, I will always tell you, fluorine just doesn't cut it, folks. We just stay away from fluorine. We just don't like it. Too electronegative. Explosive things happen. We just don't want the drama that comes along with it. So we immediately rule that out. And then we look at chlorine, bromine, and iodine. Out of those three that are remaining, once again, iodine's too big for the britches. So we focus on chlorine and bromine most. This is where our focus is at, but I will go over and tell you how to iodate a compound, how to put iodine onto a benzene ring. We can do it. It's a little different, but we can do it. So we're not ruling it out. I'm just saying that it's not very common. And chlorine and bromine are the go-tos for the halogenation reaction here. So once again, benzene is very stable. All right, so let me draw the benzene structure. There we are. I'm going to draw the full double bonds. And let's say that we brominate it. All right, well, that's Br2. That's a diatomic bromine. Brown, liquid, stinky gas that pretty much boils at room temperature. I mean, you take the cap off the bottle. We've used it before in Chem 251 if you had me for lab. And that bromine is a liquid, and as soon as you take the cap off, you'll actually start to see it just evaporate right in front of your eyes. All of that brown, noxious fumes goes right up in your nose and gives you chemical pneumonia. All right, so that's Br2. Well, if I just bring Br2 into the picture, folks, this is not going to work. It's just not going to work. Well, why not? Okay, well, let me explain. Br2 is Br, and the Lewis dot structure tells you that all of these electron dots are around bromine. There we go. And this is a nonpolar molecule. It's equally shared on both sides. It's nonpolar, nothing really fancy going on with it. And because it's nonpolar, then that means there's no full-blown positive and negative, right? And then you might say, well, wait a minute. We learned in Chemistry 251 that London dispersion forces could happen. Well, that's true. London dispersion forces can happen, which basically means that randomly at a point in time, we could get a little lopsided negative and a little lopsided positive that forms. It's very rare, and it really only truly happens if we bring something into the picture that forces it to become lopsided like this. It can easily be done. All right, so I'm not ruling that out. I'm not saying no, but I can't rely on this to go forward. I need something like this to go forward, but I can't rely on it to do it itself. So because of that, we need a catalyst. And that's why I drew the arrow pretty large, because we need to put something up here on top. We need to put a stimulator in, a jacuzzi tub. We need these two things to interact and make product babies, and jacuzzi tubs and saunas are the best way to do it. All right, so what's the jacuzzi that I'm going to bring into the picture? This is going to be an Fe, and then I bring in the matching halogen that I decide to use. So for instance, if this was chloro, that would be FeCl3. If that's bromo, that's FeBr3. So we make a match. And that's our catalyst that makes this reaction happen. So before I go through the mechanism, I just want to give you a general overview of what goes on with the reaction. Remember, electrophilic substitution reaction. So what happens is that a hydrogen that is on one of these carbons, doesn't really matter which one, but you're going to take your eraser and you're going to go, and in its place, a substitution. What gets substituted? A halogen because it's called a halogenation. So a Br goes there. Folks, that's it. That's all. No more than this. Is that complicated? Well, you're probably looking at this and going, well, this is easier than the first set of reactions that we learned back in Orgo 1. Yeah, it probably is. All right, so here is the chlorine addition or version, Cl2 with FeCl3. All right, well, we still have a benzene here. Double, single, double, cause you trouble. And off of one of these carbons, it doesn't matter which one I pick, you're going to take your eraser and you're going to go. And then in its place will go a chlorine. That's it. That's all you got to do. The FeBr3, this is probably termed ferric bromide and ferric chloride. A little bit of general chemistry review. Ferric and ferrous. Ferric is Fe plus 3, and bromine is a -1 charge. So we need 3 of bromines to counteract that positive 3 charge that the iron brings to the table. So FeBr3. Chlorine is the same way. Chlorine carries a -1 charge. We need 3 of those, and that -3 balances out that positive 3. FeCl3. So, in this reaction, we're taking benzene, we're reacting it with diatomic bromine or diatomic chlorine in the presence of ferric bromide or ferric chloride, and we are producing bromobenzene or chlorobenzene as a product. Do you see what just happened? I always love it when those moments come together like that. I'm talking fancy. I get to sound smart. I get to use terms and things that we've just talked about a couple of videos back as far as nomenclature goes and stuff. I mean, all of this just kind of mushes all in together, and it makes me feel real mushy inside when it does. So this is the halogenation reaction at the face value, folks. That's all that this is supposed to be. Now, I do want to talk a little bit about mechanism. I mean, this is organic, right? We need to talk about why. You know, I just told you that bromo and chloro I can't rely on. I can't rely on them to make this Y positive piece, this positive electrophile to go into the benzene group. They need a little bit of stimulation. They need a little bit of help, and that was the jacuzzi tub. Why does the jacuzzi tub work? Why does the FeBr3 work out? Why does the FeCl3 work out? Those are the questions that we need to answer in organic. So let me show you what goes on. We'll talk about the bromo. It works the same for chloro, right? If I do it once, there's no sense in doing it again. They all work the same way. It doesn't matter. Well, I'll just go ahead and put the chloro down here. So here's diatomic bromine, Br2, Lewis dot structure, nonpolar. I don't see no positive. I don't see no negative. And it's because it's not there. Both nonpolar. There we go. Well, I just told you that FeBr3 is going to be mixed into the system. And FeCl3 will be mixed into the system. Something's going on here with this ferric bromide and ferric chloride. And this is what you need to realize. The iron is in a relationship with 3 bromines. I'm just going to draw them this way. No Lewis dot structures. I'm just doing this as an illustration. 3 bromines. Once again, organic chemistry is a love bar. Could you imagine being in a relationship with triplets? Oh, God. The iron is in a relationship with 3 identical atoms, and they grew up in the same family, and the only thing that they do is Want. I mean, that's all that they want, right? They're electronegative. That's what electronegativity means. Bromo is over there close to fluorine, which is the most needy out of the periodic chart. And bromine, the only thing it does is sucks all of the dollars and cents away from iron. That's all it does. And iron is stupid enough to be in a relationship with all three at the same time, thinking that they're all okay with it. Well, this bromine's going to pull away, and this bromine's going to pull away, and this bromine's going to pull away, and we get this polarity that begins to happen here. And because of that, the iron is going to end up being positive. And because of that, this bromine looks and says, you know, I could be kind of negative here. I mean, there's a positive charge. All these other bromines are in on it. All of these other bromines are getting what they want out of the relationship. Iron's providing it to them. So what about me? What about me? I want it too. So we see an attraction here that goes on. The same thing down here with the iron and the 3 chlorides. This is going to create a positive. This catches the eye of the chlorine and says, hey, I got some electrons. You want a hubba hubba? And we see an attraction that begins to happen. When that goes on, this bromine actually wants to make itself more attractive. It wants to fit into that 3-way relationship that will turn into a 4-way relationship. And when that goes on, this bromine begins to suck electrons on that end of the molecule away from the other bromine that it's attached to. And when it does, London dispersion forces said that it could happen. Dispersion forces says that it could happen. That is how we create the Y positives. It's all due to the ferric compounds that we throw into the system to get this to go forward. So bromine at face value and chlorine at face value, nothing special. London dispersion is there. Electrons can shift and get lopsided on one side of the molecule, but it's going to rarely happen. And if it does, it's going to be a very quick case of lopsidedness. Hardly anything, hardly any time for this to be exposed to the benzene. But iron, the addition of the ferric, changes that whole perspective. That bromine's dirty. That bromine's filthy. Chlorine's the same way. They're going to look at everybody and try to take advantage of everybody that they can. And in addition to that, they're ugly too. I mean, that's why they were very good leaving groups. Nobody wanted them around. And one of the reasons nobody wants them around is because they want. But that bromine's going to take advantage of the iron. The chlorine's going to take advantage of the iron. And it's going to say, hey, you know, hello. Everybody else is getting some. I want some of it too. And when that happens, it really distorts the diatomic atoms, and we do see a polarity distribution due to that action. And that is how we generate the Y positives that are needed for this to go forward. The other thing I need to say, we keep talking about ferric, bromide, ferric, chloride, right? These are catalysts. They do get thrown into the mix that creates the jacuzzi tub for these reactions to happen. But in these reactions, we generally generate the ferric halide as we need it. So the way that we do this is we just dump some iron into the halogen that needs to be used. All right, so this is something that we typically create as we need it in situ, right? We create it as we need it, and that reaction will then take advantage of it. Now, does that mean that I can't get ferric bromide and ferric chloride. I didn't say no, but in these reactions, as we do them, it's going to be better if we make them on the spot as we go to make sure that they're fresh. I mean, that's, the same kind of thing you do in the kitchen. You just want to make sure sometimes things are fresh. You don't want things to stay on the shelf for, 4 or 5 years and then go to it and think that it's still going to be good. It's probably not going to be. It's probably going to get moldy and it tastes nasty. And if you got dinner guests, nobody's going to want to come to your house anymore. And the same thing happens in organic. Nobody wants to come to your organic house anymore because you don't know what you're doing. You're using expired chemicals and you're using old, crappy little things that nobody wants. And that's why your products are not turning out the right way. All right, now, the other halogen that I told you that we would talk about is I2, iodine. And I told you that this is a little different. The reason that this is a little different is because iodine is so big and bulky, okay? The ferric iodide is a little bit harder to obtain. I'm not going to say impossible, but there's just a better option out there for it. So in the iodate version iodidated version of benzene, same kind of thing, benzene reacts with I2, and one of those hydrogens get replaced with an iodine. I mean, that's the halogenation of the iodine. But we need a different type of catalyst. And the different type of catalyst here is going to be a little bit of peroxide and a little bit of acid. So this conceptually kind of does the same thing. It persuades the diatomic iodine to get lopsided, and we get a partial positive and a partial negative, and the partial positive attacks the benzene, breaks the double bond, iodine goes on in the addition, forming an intermediate. That intermediate then reconfigure the delocalization, a substitution begins to happen, and pop, off we go with our iodobenzene as a product. Whether you realize that or not, that was a mouth of another organic. It's quite a bit to take in there, right? But once again, we're learning words, we're learning processes, we're learning organic, and this stuff is becoming more and more common. So as I always tell you, go back to day one and think about, could you actually understand this if we didn't talk about any of the lecture material? And if you could say no, then that means you're doing your job and you're learning, and that's what this process is all about. All right, so there is our iodide version of getting a halogen, in this case iodine, onto a benzene ring. It just requires a little different catalyst, and that's it, folks, nothing more. All right. One of the reasons that we talk about iodine is because this is strongly tied to your thyroid. So if I want to spend this in a little bit of health, a little bit of biology here, maybe a little bit of biochemistry, who knows? But, one of the things that our thyroid does is it uptakes iodine. And that is why we typically buy things like iodized salt. This is a way that we can ensure that we get enough iodine in our diet. So whether or not you realized it, you were probably looking at your salt containers, not thinking of the word or looking at the word iodine on it, and you were buying salt, but that salt also had some iodine in it mixed in as well. So this is our way to ensure that you are getting enough iodine in your system. Well, there's also an amino acid. And this amino acid is called tyrosine. And that's what you're seeing over here on the left-hand side. So this tyrosine is an amino acid. Amino acids, amino acids actually hook up to make proteins in your body. There's about 20 some amino acids that are out there. They all have different R groups. And what I mean by R group is that they all have something in common, and that's a carboxylic acid piece, C double bond OOH. This is carboxylic acid right there. So amino acid, acid, carboxylic acid. Amino group is going to be an NH3 group. So all of the amino acids have the same structure right here, and this piece is what's different. So this is the R group. It's a random group, and there's about 20 common ones that we see that our body uses, and tyrosine is just one of those 20 plus that we actually work with on a daily basis. So your thyroid and your metabolism works like this. We get tyrosine from things like shellfish, right? And some other dietary needs. This is an amino acid protein source. That tyrosine is used, and that tyrosine will be used in conjunction with the iodine. And look at what we do here. Your body iodates the benzene ring. That is how this process works, and this boosts your metabolism, and this thyroxine will come into play, and it will help you break down things like fats and carbohydrates and all of the other energy sources that we take in through our daily food intake. If this gets wonky, then your thyroid could get wonky, and that's because the thyroxine is not producing the proper way, and we have bigger problems at hand. But look at the structure of thyroxine. Here is the carboxylic acid piece. Here is the amino piece. So all of this is part of the amino acid that was there. This CH2 with a benzene ring. Look at this, CH2 with a benzene ring, right? Look at what we've done. Your body has iodated that ring system, and that ring was a benzene ring. How did it iodate? Well, folks, that's a whole part of this production of thyroxine. Does that mean that I'm using peroxide and sulfuric acid? No, it doesn't mean that. This is a way that we can do it in a lab, but that doesn't mean that that's the way that your body does it. It's more efficient. It uses different resources than we have in the lab. So here is a way that we can kind of relate this to real life, and it's all tied to your metabolism and your thyroid. Not enough iodine? Folks, we get slow learners typically in children. So I've had plenty of people in the past that probably have had thyroid or lack of thyroid or lack of iodine in the classes that come through. No, I didn't say that. No, shame on me. No, for the most part, we have plenty of iodine folks sitting in our seats in our class, and you probably had enough iodine as a child too. But the lack of iodine can cause some health concerns, and this is one of the health concerns that comes with a lower level of iodine in your daily diet, which is why they iodate things like salt, which is commonly used for multiple purposes. All right, so that's where this video is going to stop. In the next video, we're going to talk about the next reaction, and this next reaction is called nitration. So what is nitration? How do we nitrate a benzene ring? What does it look like? Is it going to be any more difficult or as easy as the halogenation reactions? So that you'll see next.